Facebook has an amazing amount of information on people. And it's strange because like even if you are not on Facebook at all, people have tagged you, right? Thinking that, hey, I bet they're on Facebook, let me tag him. Apparently not. Oh well, it's fine. But, yeah. So Facebook probably knows what you look like anyway.
How well would it recognize the walrus degree?
There's an idea. We can start that. That's the true rationale behind the Lollerhead theory.
You want to start hashtag Lollerhead?
Okay, let's see. So we are broadcasting. So today's lecture topic is hashing. So hashing, super duper critical part of modern crypto. I mean, this is one of the must-have algorithms. It's actually probably it's used for a broader variety of stuff than secret key crypto. Right? I mean, what we think of as like normal crypto stuff like this. Right. So a hash algorithm basically, right? It makes hashes of things. So hashing is used in all kinds of places other than crypto. Typical places. How about just not? I mean, like you've seen hashing probably in some other class.
Git uses it a whole bunch.
Yes. Say it again.
Git uses it a whole bunch internally and just everywhere.
Yeah. So like there's this thing called a hash table. So right, take a data item, like come up with some number, right, and that's its location in the hash table. Right, so simple. So lots of places where hashing. Right, the idea of the hash is that if I change the message, it changes the digest. So I hash function turns message into the digest. So like in the case of Git, right, the message is the file you checked in, and the digest is the sort of identifier saying like what revision you're at for that. So Git can notice that, hey, he's changed his file because suddenly the hash is different. So we want two things out of hashes, right? We want so for cryptographic hash, you care about this. For just a hash table hash, all you care about is collision resistance. You don't care if it's like easy to figure out based on location of the hash table what the value is. That doesn't matter, right? But what you want is you want to make sure that different values show up in different locations. That's collision resistance, and you really want to have preimage resistance. And preimage resistance just says it's tough to take the hash and reconstruct what the message is. And this is for the uses of hashing, and these are actually different enough that there's some crypto like hashing algorithms are targeted toward one or the other. Usually this one's considered more or less easier. So for example, if I want to keep my connection to www.cs.uaf.edu secret, I want to know that there's not a man in the middle attack or a woman in the middle. I want to know that there's nobody basically. So I can lots of algorithms out there that haven't done that yet to basically to know that I'm communicating securely with somebody at the other end, which is awesome. You are communicating securely with somebody at the other end. They may be evil, right? So the typical thing is that your computer, right? So here's you, you're Alice, and then Eve is just sitting in the middle, and everything that you try and send, right? It actually makes it to Bob, but it makes it to Eve first. And this is the ironic part is that you can have all the crypto you want on your link to Eve that doesn't help you at all, right? Because she's basically reading everything, and she can actually put the same crypto. I don't even know how to spell crypto. So the same crypto basically on the link to Bob, and that's not going to help you, right? Because it's decrypted in the middle. So man in the middle attack. So how do you prevent that? Well, there's this certificate that says how does this actually work? So we've got they updated this. So uaf.cs.uaf.edu, and John Kwan just reset this thing. So we've got a SHA-256 checksum of this information, basically saying in common RSA server says that cs.uaf.edu is run by Alaska Statewide, and that they have this public key, etc. Right? So in other words, this is saying University of Alaska runs www.cs.uaf.edu. Here's this cryptographic stamp saying yes, that's how we do that, and then that's actually delivered by in common. Who the heck is in common? Well, They have a certificate issued by the User Trust Network in New Jersey, which of course everybody inherently. Now let's see. Apparently, you don't inherently trust Ad Trust. User Trust. You trust Ad Trust. So Ad Trust is built into your browser, right? Browser ships with, unfortunately, like 100 of these built-in root certificates, and they just say, "Yep, Ad Trust. They're good people," right? And there's really not. It's issued by Ad Trust. At some point, your chain has to stop. AdTrust signs a certificate for user trust signs for InCommon, and InCommon signs a certificate for WWCS. The way all of those signatures work is that what they do is that they have actually basically just RSA encrypted a SHA-256 hash keys thing. So really common, right? I will hash a certificate. Anybody know how hashing is used in Bitcoin?
So as a miner, I get to choose what's in the block. I assemble things in the block. I hash that block with a nonce at the end. That produces a hash that satisfies requirements, and that becomes the new block, right? And then to link back the old block, I have to have the previous block because that's the blockchain. Yeah, it's the same thing.
Yeah. So the culprit of Bitcoin, they want to make it hard to rewrite history and say, oh no, he didn't give his money to him, he gave his money to me. That's what really happened, right? That's what you want to not have occurred. So the public ledger, the basically records what occurred. But the way that we actually validate saying, like, this is the stuff that really happened, is we come up with a number at the end that gives you a hash with lots of leading zeros. That's what Bitcoin mining is all about. It's finding hashes of lots of leading zeros by changing the bracket at the end. So we know of no better algorithm for doing this than just trying lots of hashes, right, and seeing how many zeros you get. And at the moment, it's like an absurd number, like 50-some zeros or something. It's a large number. In other words, only you have to try to do the 50th possible nonces before you find that some block winning thing, right, which is an enormous amount. Winning a block is worth like 5 grand, it's 25 Bitcoin, which is a big number. So the deal is this is something lots of people are looking for. There's lots of efforts gone to finding these hashes that actually like validate what has happened, really happened with Bitcoin. And the trick there is that hashes are just hard to compute, right? It's hard to. So what I want to digest lots of leading zeros, and nobody knows how to structure your message to make that happen. So this is something you're trying to come up with. If you're targeting particular hash, you may make for Bitcoin means those hashes. I mean, I think the biggest of hashes. I take my password, and you always have this problem. If I've so you knock on the door of the secret secret revolutionary entrance, and you say, I would like in because I am a secret revolutionary. What do they say on the other side of the door before they know they can open? How do they know you're not a government agent? They say, what's the password? And you say, well, I know what the password is. Do you guys know the password? Because I don't know if this is really the secret revolutionary headquarters or if you've taken over the government. Right. So the question is, if there's only one password, one side has to say, the password's cheese. And it's like, yes, it is. Great. Now we both have authenticated each other. And it's like, well, wait a sec. If you just broadcast the password in clear text, there's no easy way to actually validate that, like, you didn't know that the other side didn't know the password before. This is a big problem. So similar deal, right? You don't, your web browser, I'm amazed that this is the case, can actually just literally send the password, HTTP authentication, to a web server and say, he knows the password, it's cheese. Right? You just revealed cheese in clear text, essentially. I think they put it in base 64 or something, like not encrypted at all, but just enough where you're not going to accidentally see the password. So HTTP basic authentication, Netrun used this for like a decade. Actually, Netrun still uses, just now it's all inside SSL, so it's encrypted to hell beyond before it goes across the network. So you can't just send a password across the network. Is it safe to send a hash across the network? Yeah, so they can, the idea is the problem with just sending a hash is that now the hash can be used as an authentication token. So what do you, so actually the process for doing this actually gets kind of hairy. Typically what happens is server says, take the password, hash it with 73, and tell me the hash. And then you say, well, you take the password and you hash it with 16 and tell me that. So you basically just tack on some random crap at the end. Now what so each side is going to basically compute the result on the other side, and if the hashes match, you just mutually validate, and each side knows the secret without revealing the secret. Super important thing. Right. So this is common, and there's also some protocols for this that we will get into.
This depends on the hash not being.
Yeah, so the problem is that the hash is reversible. I mean, what you just did is you just took the password and tacked on 73. There's lots of ways this protocol can go wrong. Like the server can say, you need to tell me the hash of the password plus 76. And the client says, yes, you need to tell me the password first for the hash of the password plus the random number like 76. Oh. That's easy enough. So right. So making sure that the randomness is So we've got so hashing protects passwords. Actually, typical best practice. You some types of password, it gets hashed on the browser and then shredded, and you take the hash, and now you take like the hash of the hash, and that's what it's actually typical of passwords. Actually the HTTP digest authentication. You put that in the hash, and now you actually there's nowhere you put it in RAM. Right, somebody can be just like scanning through your browser's RAM, and the best they can get is the hash of the password. That's still kind of dangerous because the hash of the password, I mean, you can check to say, is it password? If I hash password, does that come out with? Right, so no matter how good the hash is, it's always possible to say, if I know the digest, well, was the password password? Was it 1, 2, 3, 4? Right, you can try multiple messages and see if the digest match. If they do, then you're screwed. It's not perfect protection. In fact, it's always possible to just brute force all the possible messages and find the digest match. And that's going to be a thing. There's no real way around that. But the problem is you can make that right. If you get like a 256-bit hash, like typical hash of nowadays is SHA-256. 256 bits is such a huge space that unless you know something about the message, it's really hard to. That search space is so enormous you can't really. So let's see. So you're really not pretty much resistant, but it turns out to be really surprisingly easy to do. Like there's some hashes like MD5 are just totally broken as far as collision resistance. They can just manufacture collisions all they want. They can come from lots of different messages at the same hash rate, which makes it. That grammar resistance actually seems to still be okay. You can take an MD5 hash for password, and our most efficient known way to figure out what the password is just try the passwords and MD5 hash them all. It's doable, but it's just very time. So about collision resistance, why do you care about collision resistance? Well, I've got here a digital signature that says www.cs is officially right now. Any browser can look at this stuff, look at the certificate chain, and say, yeah, his hash matches. I have a cryptographic signature. Right, this I take the hash of basically all this variable length stuff, and I say this issuer has agreed that this guy actually runs right through that. Universal Alaska actually runs www.cs. Right, they have a legit authority. Right. There's an example where if your hash algorithm here's MD5, and you can like make up new, you can make up new subjects and such, and have the hashes match. You can actually come up with a certificate that says like, oh yeah, I'm Google.com. Even if you're not Google.com, right? Whoever signed this has no authority to sign for Google.com. And they didn't. They signed something totally different. All right. So the idea is hash collision is really bad because you can get one thing signed, what they're actually signing is the hash, and then you can actually substitute another different thing, and then have that suddenly actually the hash will match as far as anybody can tell. Right. I present that forward certificate to a browser. Browser checks the hashes, checks the signatures, everything matches. Right. There's no way of telling really that something that wasn't really what they signed. So there's an awesome example of this. So again for MD5. So I want the MD5 checksum. Nice little command line program does the MD5 checksum of anything you want. If you want to know if your LS executable has been changed, take the MD5 checksum bin LS, and that's if somebody's modified your executable, tack out some crap at the end. This number is going to change. Collision resistance. So I look at, I do an MD5 checksum of all the PostScript files, and this was done a few years ago. So PostScript files, so I have a letter of recommendation, and then I have what tends to be order. They have exactly the same MD5 hash, which is surprising. Because if you look at one of them, this is a letter of recommendation from Julius Caesar saying basically, oh yeah, this lady is, she's really good. She translated Roman Empire documents into Gaul. Gallic, excellent letter of recommendation. Please hire her. This is great. So this might be straight from Julius Caesar's desk, right? Now the trick is maybe there's the stamp, the modern equivalent of the ink stamp saying I'm Julius Caesar and I really wrote this. Might be a hash of Julius Caesar, his signature and this document, right? That maybe this thing gets published in the the imperial register saying official things, right? If the hash matches, and it's more efficient to just publish the hash, right? Less characters. It doesn't reveal the contents of the letter. So if you have some secret letter saying like, yeah, you need to kill this guy and this guy and this guy, then you don't really want to just publish that, right? And then it's a lot easier to change those things. So you might have a hash chain, right? And there's lots of tools that are to authenticate based on this stuff. So this lady might have forged a letter saying the following, right? Yep, all imperial secrets about Gaul are to be just handed over, and this is just straight from Julius Caesar's desk. And again, the difference is surprisingly subtle, right? If you look at this thing, poster file. So it's a poster file with like the text of the document basically going to the places where it's supposed to go. And then at the beginning of the progression, and then that doesn't really So the trick is this binary gibberish has been carefully chosen to make the hash work out to be the same. MD5 is broken in the sense that that binary crap, there's an algorithm for coming up with binary crap that makes the hashes come up the same. There's no algorithm for efficiently finding the binary crap that would make, say, SHA-1 hashes come up the same, although there's on paper, that there's an attack that's approaching feasible. It takes 2 to the 60th, 2 to the 60-something plain text. So SHA-256, we don't know of anything better than just trying, 2 to the 100th or more possibilities. So the deal is, you might think, I mean, this is a little bit frustrating because a lot of people look at this and they say, well, clearly that's no good, right? Don't allow things like this in actual messages. But unfortunately, there's so many possible. There's lots of sources of entropy that people don't, and there's you have to inject some entropy to actually be able to match hashes typically, right? So if you say, well, look, if I have like a digital signature, where's the opportunity to inject a bunch of entropy? Not very on. Right? It doesn't actually have to be binary entropy, right? That's just that makes it slightly more efficient. Do this stuff. It could be anything, right? So people often claim like, well, collision resistance isn't that much of a problem in practice because you can usually look at an image and you look at a document and you say, well, this is binary garbage. It looks really suspicious, right? It doesn't necessarily have to. In fact, typical examples of contracts. Right, so you might publish, like in the newspaper, you publish a contract saying, like, B and G have agreed to this contract, and the contract maybe says, like, G is going to give you light bulbs, right? Some trivial thing, and you have secretly like chosen the structure of the document so that you can come up with an alternate contract that says, like, yeah, G is going to give me $150 million a year, and then you're going to sue G saying, hey, where's my 150 mil? Right? You agree, there's the contract, right? Hashes match. Now, the deal is like there's no opportunity to like put in binary garbage in apparently in a Word document there's like millions of places to hide it. Right? If you say plain text file, it's what it's got to be. Our contract department requires this, right? Because there's no funny business, right? What do you do? Well, you have an address, right? You have the zip code, right? This and then the zip codes, are actually legitimate stuff. You have like names maybe of sub corporations, right? It's a shell corporation. You're going to pay it to the bank account number of binary garbage, right? If that fails, you have to pay it to the real bank account. You have a contact me, a telephone number, whatever. Right? Lots of places to inject some sort of changes here that might be really hard to after the fact realize that hey, this is the situation for hash codes is actually pretty. Apparently, cryptanalysis of secret ciphers is in a lot better shape and it's still pretty bad. I mean, the MD5 people were using like 10 years ago, and there were hints that it was maybe possible to come with one collisions, but it was as about 9 years ago they realized like we can like write a little program that just spits out as many collisions as we want with customized. So suddenly the things broke entirely. MD5. So MD5 signed digital certificates were accepted by browsers until like 2010. Right. So it's kind of bad news. SHA-1 is actually sort of in the same situation where like there are known attacks. They're just hard, right? 2 to the 16 is a big number, especially when you store it. It's not 2 to 16 times 2 to 16 bits. But it's sort of just a matter of time until somebody's going to crack SHA-1. At the moment, here I have 2 files on my hard drive that's the exact same MD5 hash. And of course, they're going to have totally different, if I do a SHA-1 hash of those files, they have totally different SHA-1 hashes. If I have a SHA-256 hash, they're going to have totally different SHA-256 hashes. But that's what you would expect. Now, it's certainly possible to imagine having 2 files that have the same Isn't it inevitable? So collisions, right? 2 files that have the same hash. Could we come up with a hash code that doesn't have those? Because those suck, right? That's no good. Just totally collision-proof hashing.
We do. They're like zip encoders. Any compression algorithm.
Yeah. So there's this interesting theorem, right? This is straight out of the pigeonhole principle. Oh my gosh, that whole concept. How many files are there that have 2d6 bits? 2 to the 2d6. So if I have files of length, say 1,000 bits, there's 2 to the 1,000th of those files. Big number. If my hash is 2d6 bits, that's a much smaller number. So what that means is if every file has a hash, there have to be more than at least one hash has to come from more than one file. So yeah, so like I mean we have these 2 properties we want. We want total pre-image resistance, right? You cannot figure out what the password was. So it's easy to get that, right? You say like, yes, the hash of any message is 0. Recover that. Right? That makes it harder than we have perfect pre-image resistance. Right? No way to find a message because all the digest are equal. But unfortunately, they all combine. So it turns out for passwords, you want pre-image resistance to keep them from recovering the password. You've done that. If you want collision resistance, why do you want collision resistance for passwords? Using a hash algorithm, everything's 0.
I mean, that's a password.
Yeah, it's all good. Passwords are all interchangeable. I mean, you need the password. And okay, yeah, great. Yeah. Okay. So we want collision resistance to keep other people's passwords from working. And it's funny because both of these things are kind of a little bit negotiable. Right? Occasionally, like 47 characters binary gibberish works as a password just as well as 1, 2, 3, 4. Okay, that's not really that big a disaster. So the collision resistance, as long as it isn't the case of like tons, there's like 50 alternate passwords that are all shorter, as short or shorter. Yeah. So other ways you can get from collision resistance. The hash code of message is the message. No collision. That's one of the few ways to get there. But what that means is that you have no failure resistance, right? You want to know what message is? There it is. So it turns out that, again, mathematically, I got a cipher. Takes a plain text and a key, gives me some ciphertext. If I want to convert a cipher to a hash, I'll do that. So I have a message. I clearly have to put the message in one of these two inputs. Yeah, so say I put it in the key. So what I'm going to do is I'm going to encipher zeros using the message as a key. I'm going to get some value. The question is, how are you? I mean, if you have a cipher, there's a decrypt operation somewhere, which is scary. So how can you decrypt it? Because we're going to publish this, right? That's the ciphertext we're going to publish. Somebody can decrypt it if they know the miss get zeros.
What if everyone knows? Oh, to get zeros, we don't care.
Yeah.
Oh, you got zeros.
Yeah.
You put it in the key.
Wow, you got zeros.
Congrats. Awesome.
So it turns out this actually works quite well, right? In fact, this is the standard way to convert a secret key encryption algorithm into a hash algorithm. Encrypt zeros using the message as key. What if we did the other way around? Take the message, encrypt it with zeros as the key. Unfortunately, not anybody can decrypt this ciphertext using zeros as the key and get the message back. You just only so you can also, for example, take the message and use itself as its own key. I don't know what. If you do the key, you can decrypt it and get the message back again.
That's right. Yeah, the note in that.
This is sort of checks. So the big problem with this in practice, the data size for most ciphers is kind of unlimited, but the key size is usually where do DS, for example, 56-bit key, that's how long the key is. Sorry. If you're trying to hash a message longer than that, what do you have to do? So you clearly have to work in multiple chunks, yeah? Chunks of 56 bits at a time. So what do you do with the chunks? So I take the little sub-hashes.
You could just use them separately, or you could feed them in.
Use them separately is an interesting idea. So it turns out Microsoft famously totally screwed this up. The LM hash, or LAN manager hash from way back when, it takes your password. You have an awesome, 15-character long alphanumeric password, which is great, right? Very hard to brute force. It's so big. They DS hash this thing, right? So they take hash of zeros as the input, the first 7 bytes of your password as the key. They publish that hash, which is totally wrong. They take the other half, they hash it, they publish that hash. Those two hashes both have to match. Here's a big problem. You've just made it. I mean, you've taken the square root of the complexity of like brute forcing these things, right? They can check to see if they got the first 7 characters of the password right. That pretty much destroys your security. So in fact, 7 characters is enough that so you can just make a table of all 7-character passwords right now, and hey, now I can crack anything more or less instantly, right? Anything you can type at a keyboard, right? That you've lost now. So this was really a disaster. They would have been way better off, right? If all they would have to do is sort of there's the first half of the message, and you do another stacked cipher, right, where I take the second half of the message and combine it. So just encrypt the first half, and then use that as the key to encrypt the second half. Right? So you can repeat this indefinitely as long as you nest it. Right? But the problem is if you don't. If you just publish chunks of hash separately, you're in big trouble. Thought experiment. Sitting on the wall, you have you punch in the code to access the secret facility, right? It's a really secure facility, so it's binary, right? Because they realize, if you have numbers there, right, like the 9 key is going to get used 3 times or something, you look at the smudges, so they say, okay, binary. I mean, if you only have 1 button, then you have to press it a reasonable number of times. So you have to press the thing 64 times, right? 64 presses, right? So you enter some binary string of gibberish. Both buttons are natively smudged. Life is good, right? So really hard to crack, right? 2 to the 64 possibilities, right? And of course you get them, but after 100 failures or something, then the fix are coming. What happens if you have the little lights, right? And as soon as you enter the digit wrong, the red light comes on. Suddenly you don't have 2 to the 64th possibilities anymore. Suddenly you can crack that sucker in 64 tries. Worst case. Isn't that weird? I mean, so this is very surprising, and yeah. So intermediate results are really disastrous. You really want a hash that basically just says, bam, there's the whole hash of everything. Right? Because the problem is, if I pull some hashes that I publish independently, that means they can crack it. I mean, again, worst case, if you take like the ones and zeros involved in the key and in the password, and you hash them independently and publish the hashes of each one, they can independently crack it. Is the next digit a 1 or a 0? Duh, right? There's like 2 options. It's really easy to brute force, and then they can just they can work their way across.
There's no wireless attack. It still works.
This
So
is
for-
yeah. There are
wireless-
so many of these.
So
Yeah,
VPA2, like really good crypto,
Yeah,
great crypto, has this really bad problem on some routers that in order to make like syncing two keys together easier, they like push a button on the router, you push a button, you're sync properly. It's all magic.
Yeah.
The problem is that if you're just brute forcing it, like you do half of them, it tells you the first half of the random that it generates is right. So you're just like,
No. The first half is totally wrong. I
and then
didn't
the
look at
second
the
half,
second
and so it
half.
takes like, I've done this, I did this like a work hotel, I did it like 15 minutes.
And the thing is, it doesn't make it twice as fast to crack, right?
Yeah.
It makes it like the square root as fast, right?
Yeah.
I mean, the 1/2 is going to be exponent, not multiplier. So big problem. Yeah. Don't do that. That's really bad. And it's surprisingly hard to figure out how to do this, right? So if you're writing the firmware, if your microprocessor is sitting there watching for buttons on the key presses of your wall, this is actually surprisingly tricky to do, right? You're like, I have to record the fact that this was not the right key and then tell no one. I have to act exactly the same, right? From that point onward, I have to keep accepting keystrokes until finally, whatever the link is, until they press like the go button. I revealed nothing. And it's quite nice. I mean, because you could imagine, so the slightly more sophisticated version of this thing, right? As soon as you press the button wrong, the firmware just says like, he's wrong. It's just like, no. If the circuit does anything different in the case where it's going to work or it's not going to work, you might be able to detect that. Right now, it's like they might have like an inverted power meter sitting in the wall, watching the wires go in, and as soon as it's like yeah. Oh, right. As if any emotional state inside the circuitry is going to like totally reveal the key, like within a very small number of tests. So this is it's making that movie, the whole movie like sequence where they like take apart the keypad and they're like measuring things and they're like really quickly find it. They're like there's some decrease in the some safety more possible.
Well, I guess yeah, you're just put it to a buffer, right?
Put it in the buffer.
The
It's
buffer
just like
comes
whatever. Yeah.
and then you check it right then.
Yeah. Actually, probably what should happen is that buffer gets hashed a couple times.
Yeah.
Then just gets sent across the network. And then the server's like, I see you tried this 7 times. Send in the dollars. But we're just like, oh yeah, the response is keep that. You should explode. Yes. Lock all the doors. Yeah. So I don't know. Tricky to set these things up. Okay, so we have so questions about the sort of basics of hashing, like the model for what we use hashes for. So I mean, in practice in crypto, it tends to get used in one of 2 places. One is in which you have variable linked data, and you don't want to deal with variable linked data, right? Because the big problem is people's passwords, for example. Right? This variable linked characters in there. It's going to be, some of it long, some of it short. It's just that there's all sorts of junk you don't deal with that. And the nice part of dealing with hashes, everything is fixed. You use SHA-256. There's 256 bits in it. There's no doubt about that. So that's really cool. So we converted our variable length data to fixed length data. And the other big advantage was we're actually one level removed. This is so we protect the message at that point, at least some. It may not be perfect, but it's better off. The advantage of being one level removed is if there's a possibility of like gaining whatever counts by having very carefully chosen. so for example, the RSA signature, right? And we're about a week away from doing RSA for real here. The RSA signature is used in all this stuff, right? So you look at this. So this is RSA encryption using RSA encryption actually has these amazingly poor performance out of that. And the reason is exponentiation. So the deal is, if they can get you to sign, a number and 1 plus the number, the difference between those two signatures is your private key, which is really bad. So right now it's basically chosen plaintext attack on RSA is totally a known thing, and this means RSA is totally unsafe to use on just random data, right? As if you take RSA encrypting passwords or something, so you send them out, that's actually a terrible idea because someone will just basically say password 0, password 1, boom, right? We got you. Whereas so standard thing, right? The only thing they ever RSA sign is like a hash or a random secret key, so that there's not going to be any differences, not going to be a perceptible set of differences between them. So right, I mean the SHA-256 is actually protecting the RSA encryption. Right. Show, let's see. So we got pigeonhole. Yeah. Okay. Good. Don't use it. So SHA-256 is basically pretty much okay modern Cipher. There's some talk that maybe we should switch to SHA-3. At the moment, it's kind of SHA-2, SHA-3. But there's a slightly different design to the things. But SHA-256 is pretty good, and it's actually pretty simple. So here's the code, and this is all the code except these bizarre crazy tables. Here's the data. Here's a chunk of the data we're trying to. This is what you're trying to hash. And basically, all that's happening, we pull in the next chunk of. So we get the W's. The new data is coming in here. We have a fixed round key basically here. We just can process. And we have and this other state variable, so you can see that there's kind of a shift by 1. That's the shift upwards.
I had to count like 4 times to be sure.
SHA-256 would require these. Yeah.
Start at 0.
Yeah, so you know what's happening here is pretty nice. We have these really silly, so that's XOR and they're so the deal with these is everything. So if you leave these out, this is all reversible. And we're doing like binary sum of known values. I guess that's the second A against itself is sort of shredding some of this. But the deal is the XOR typically reconcile your word that we're still. So the nice part is this is destroying data. It's destroying data for the known fixed. You see the ones in A's that are those flat. So basically, right, scrambling, and then these are the big mixing skills, right? That they're mixing skills. So it's basically this, there's one that takes the right half and mixes it all together, and there's one that takes the left half and mixes it all together. All this stuff it's all XORed, functionally XORed, and then the result is now there's an intermediate result that actually goes into So she'll scramble, and this looks pretty similar to a secret, like an encryption algorithm, with the difference being that a lot of these operations are reversed. They are actually destroying data. And this is a feature of the hash. You want that to be effective. It's inevitably you're going to have collisions because the messages are longer than the output, but you want to make sure that it's not going to be possible to take a shortcut password and then just run the encryption algorithm back there, run the hashing algorithm backwards and forwards. So, for example, right, if you want to win all the bitcoins, basically, if you could just say, I want basically A through D would be fine. All these zeros, and this would give you 128 bits of zeros. I think you would win every Bitcoin block. If I want those to all be zeros, what do I have to have? Well, in the previous iteration, A, B, and C all have to be zeros. And here's where it gets hard. The result of all this has to be zero. How do you get there? Well, unfortunately, there's like a lot of ways. Well, right, we can pick any set of inputs we want. We just want to make sure that after 64 rounds of this, you get 0, 0, 0, 0. This is not really rhetorical. I would love for somebody to say, well, can't you just... Because then we could, I mean, I'd be fine. We'll stop at $1 million a piece. For everyone in the room. It wouldn't take that long, right? Every 10 minutes, somebody wins a Bitcoin block. Right? Bitcoin block is worth like $5 grand nowadays, so $5 grand every 10 minutes is good money. So if we're making 60,000 now, $1 million is probably important. So there you go.
I'm just testing your data flow.
Yeah.
Okay.
Simple data.
Whole day. Yeah.
Really, the just word.
Now we know how many Bitcoin you get per block now. Probably less.
Or was it? I thought it wasn't 25. Was it constants? It was 50 the last time I taught this class.
Yeah. Well,
And then it dropped down to
it
25.
has every so many blocks.
It's about to drop to 12.5. I believe.
Oh, your estimate is 25.
Yeah.
And it's an estimate for 12.5, 2015.
Oh, okay. That's
So,
about
according to some random wiki that I found. He ended up Bitcoin.it. Yeah.
Yeah. So this is actually quite surprising, right? That we don't know how to invert. And the problem is it's designed out lots of inverts. So if you want zeros out of A, there's just a million possible options, or pick one. And unfortunately, it'll be where to make that one work out. You don't know so if I say, yeah, I'm gonna get a zero because that's gonna be zero, 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 zeros for everything. The problem is you can't make the output all zero because well, we need non-zero. So you say, well, okay, so this time we need non-zeros to come out of Q, you're responsible for that. And unfortunately, the requirements are going to conflict with each other after a few rounds. So it's probably possible to come with the hack for juice versions. So run 64 times around this thing. All of the inputs are really will well mixed going. Yeah. So try the code. So here we get the code. It's this is my own, and this is actually fairly old. This was from the last time I taught this class. SHA-1 is the one that I've had for years and was using for everything. SHA-1 is looking scary now. So I basically got there's a class SHA-256 that does the hashing. I'm just going to skip down to the computation of the hashing because the interface is probably not that interesting. So we have bit rotate just like everybody else. We have some round keys, and the round keys are just sort of the binary numbers. These are all zero. It would probably be very easy to come with a hash of zero, but just inputting data of always zero. So here we have random multi-numbers. They are actually essentially random numbers. These are the fractional part of the cube roots of the first 4 primes. Take a prime. The cube root is not going to be an integer. It's going to be some crazy fraction. That's the leading binary digits of the fraction. Easy enough. And it's actually, I don't think there's anything really that's terribly important about it. The reason I chose this instead of saying, hey, use these numbers, get it? Get it? It's to prevent the sort of the worry that somewhere the NSA actually is secretly like, they're worried about the government running money or something, like, we'll just take all the bitcoins because we chose these as the output of, the basically, if you can pick these in each round, right, you might be able to cancel out whatever's happening and maintain all zeros. So don't, primes, hopefully they haven't hacked the primes. If the government's hacked the primes, we should, again, just give up. So same deal. We've got 8 state variables. So there's 64 round keys, one used for each round. Actually, we have 64. We have 256 total bits of state there, and these are the square roots of prime. So this is again a good. This is kind of a nice, kind way to sort of say I didn't do anything fancy with these. It's just pick some numbers. Let's see. So we've got. So here's the actual data. My data in the buffer, it gets loaded as a big endian integer. Everything else is going to be integers. So we loaded as a big endian. Partly just because this standard is a little bit older than. All the cool kids now are running little endian computers, right? I mean, your ARM machine, your x86, they're all little endian. At the time, it was. I mean, big endian numbers, right? The review by the number like 1. On a big endian machine, I store byte 0 of the 1 first. Right? On a little endian machine like x86, I store the 1, the low end, instead of the big end. So if I'm converting from binary data like a string, there's some ints I have to specify which end first. So in this case, the first byte in the buffer is the high byte. Big endian load. So I load up all my data into the W array. I basically just immediately can add the key. So there's the key, and this thing actually then gets scrambled. So this is just a S1. S1 is this first set of rotates, and then I have another second set of rotates. So it's just a scrambled version of the input. So basically, input data. This is the stuff you have control over if you want to. Game hack. So I pick values in my buffer. They get so that I can directly affect the first 15 rounds. Easy enough to do. And then it's the remaining rounds that's where things get tricky. Let's see. Copy over my state variables into local variables. So I get A through H, and this matches the all the images. So again, I've got the rotate. So 64 times. And the trick is that everything in there is just getting sort of continually cycled back and forth. Not clear 64 is a constant for the universe. We can probably change that. Actually, we should make a broken version of SHA here in a sec. So basically, so there it is, right? And we do this. We do our mixing, and then that's essentially the hash by the end of it. So if I take the hash of nothing. All binary zeros. It would be really cool if I got all binary zeros and no one had ever thought of that. We'll try that. That's the first thing I tried. So it turns out if you hash all binary zeros, you get that, and it's because of the keys, right? We have those round keys. So there's the SHA-256 hash of zeros, and you can verify this works because you do like. I want no bytes, no new line, no nothing. Pipe that to SHA-256 sum, and we should get E3B0, yeah, E3B0. And your probability that the hash is actually different at some low digit actually drops exponentially. So we can echo like so character A, right? So I have, there we are. Character B is 1 bit different. Wow, that's a lot of differences. There's essentially no relationship after 64 iterations. Right? There's one, so same deal. I do a D is again it's 1 bit different from A, and it's just totally different. So you can do the equivalent of differential cryptanalysis here, right? I'm gonna hash basically incrementing values. This is 1 byte of the all the bytes in the hash. But 32 bytes in my hash state. So there we are, and not a lot of patterns jumping out. Well, this is the full SHA-256. If we do a reduced version of SHA-256, like I'm going to do 1 round. So here's 1 round. We run it. This would make Bitcoin mining a lot easier. So you notice, I think is it easier to see if I'm scrolling? It's easier for me to see. So if I'm scrolling, okay, low byte goes into A. A gets, so if you look at the diagram here. So, this is the one I'm changing. Big A. Big A. That's the one I'm changing. Change that. That ends up impacting the middle one. That's what I've changed. So as I scroll back and forth here, you can see the left and in the middle, right? So there's A, and there's B, and it hurts me to see the high byte changing, even though it's the low byte. So one round doesn't actually do anything. That's enough to, I guess the really easy one would be 0 byte SHA-256. So if I take 0 rounds, I do not actually depend on the data in any way. How many rounds do you do? We do no rounds. So no rounds is going to be have a really interesting differential analysis. That is the SHA-256 0 hash of everything, because we never even looked at the data. So shame deal. So I just even if you do 2 rounds, you can actually see things starting to explode here. But as of 1 round, we were off in 2 bytes, and that was it. As of 2 rounds, you can see those 2 bytes have actually. So these are in fact the bytes that then get shredded. So after being shredded, they've impacted a bunch of stuff here, and then you notice the H is not actually impacted. So definitely, so we're now at sort of one whole word different, and in fact, I think it's over to the next word. It's slightly more than, and in fact, right. So we do more rounds. If I go up to 3 rounds, you notice there's still a few that have not been actually modified. And this is actually just because of the sort of cyclic shifting. I mean, 3 rounds is not to get until most of those columns are changing, but there's still a couple in the middle that are abandoned. If you do even 10 rounds, so we're only or if you do 6 rounds, because there's a total of 64. So this is 1/10 of the total number of rounds you're actually supposed to do. But it's actually getting to the point where it starts to be hard to predict. That they could have stopped there, for all I know. It's all fine or too. It's probably easier to determine. So you notice this thing is block-based. It takes your 16 words of data from the message, works its way through, does this sort of 64-step permutation. Here's an interesting question. If I take the hash of the message A, and the message A binary 0, do you want those to be different passwords? Because you have to assume there's a link field somewhere. So the 1 byte A or the 2 bytes A binary 0. Those feel like different messages, right?
Yeah, that was, yeah. So that's probably different.
Yeah, I mean, there's no relationship between those. But the problem is, if the way I make my hash is I put in binary zeros, and just pad out with binary zeros, these have the same hash, which is collisions you don't want.
Address field of that thing and then put whatever you want after it. Good. Zero. That certificate. That was fine.
Yeah. So it turns out they thought of this, which is actually kind of good. So standard thing, if I have a 1 block hash, if I have a long multi-block hash, this was the last block. You put the length as a 60. So the last 64 bits of the last block, I have a length field. And for some reason they put the length in bits. I don't know why. So this would be a 16-bit long message, right? So that's how long the message is. So the deal is this length field being different would mean that you're clearly going to get a different value. They did another kind of a cool thing, and I think it's because it's only using multiple blocks. So they put a leading binary 1 there, which of course in hex would be like hex 80. So if you look at any implementation of SHA-256, including mine, at the there's sort of the very encryption-looking. Basically, just load in the data into your state variables, do a bunch of rounds, hopefully the right number of rounds. If I do x64, and that's basically the new state variables. And then at the there's basically copying binary data in, so it's basically just working its way through ugly C point arithmetic. Let's see. So at the end is a lot more complicated than it looks like it should be. So we figure out how many bits was total message so far. We figure out where we are in the message buffer. See, we've got room to put back on the leaving added bits. So I basically I always add the and then I see if do we have room here. If we don't, then I have to output a whole block with so far. And the very last block is going to actually have the message that's on the message buffer. We then hash that into our state variables, and then that finally is that's it. We're done. We finally take all of our state variables. That makes the actual state of the hash. So this block operation, this is where the 64 So this is actually quite surprising for Bitcoin. Right, you have this long transaction log that you're trying to validate. Like here's the hash of the previous length of all transaction log. Here's the transactions that have happened since then. And then at the end, you take you put on your nonce and you're shooting for all zeros. It's actually quite surprising that there are implementations that are mining basically by rehashing everything, which is not what you need to do. Right? This last block may be the only thing you have to. So your state variables are going to be identical. Right? You start at the beginning. You basically work through this whole thing, and then I can customize this thing to make this one like faster. So I basically just I would clone out my state variables before I try that last block. Right? Last block, I append my nonce. I see what that turns out to. I still have to do the 64 iterations of garbage, and it turns out nope, fail. Try it my nonce. Try it again. Say, oh, that's pretty good. See if that wins. So. Questions about it? In the homework, you have to build a hash out of our Cipher. So you have to reverse the hash I built. So again, the data there is 0. The key is the hexadecimal printhead entry. Anybody have any problems with the homework?
I have. It says I've done the first two. I'm having no.
Oh, shoot, you took this class before.
Yeah. So it's probably not a big deal for the first two, but maybe for the first you should run.
Make sure you do them again.
I will. I mean, I wasn't going to try and cheat.
It's a totally different homework one from 0. Yeah, for NetRun, I really carefully thought about this. Like, okay, you'll have courses, years, homeworks, assignments, etc. And then for Cryptography, stuff. And I'm facing this. Yeah, I mean, when I first tried this, I had like, there's all these homeworks already. I'm like, wait a second, class, I didn't. Oh, it's the same one. So, yeah. Hey, has anybody completed the homework? The homework works, actually.
For me, I don't know what that
worked for Mike. Good enough. Existence proof. Yeah. So hopefully let's do Friday. Yeah. Look that up. So we're going to do some hands-on work with actual examples of things you can do with hash codes next time. So. And thanks for calling in.
Thank you. Hey, was there something different with the microphone setup today?
There's not supposed to be. Is it worse or better?
Worse.
Oh, I bet it just picked the wrong microphone. I have no idea where to change that. I have a really good external microphone, and then I have a really crappy built-in mic.
Ben, did you notice the same thing?
Yes, I did, but oh well. Yeah, I understand that happens. It's happened to me before too, where it just picks up the wrong microphone.
I plugged it in at basically the same rate, so the light is on. I don't know why it would. Actually, this This problem is I'm not totally sure. Oh yeah, internal microphone. Use that one.
Yeah. It's like
Did that immediately make it better? Is this better
You'd
now?
have to walk away from the. You'd have to walk away from the computer for me to tell.
I'm walking away.
Yeah,
Yeah, I don't know.
it does. It makes it better.
Okay. Yeah, hopefully that'll stick. I don't know if that will actually stick. All right.
Oh God.
All right. Well, thank you very much.
Yeah. Okay.